Hello everyone. Welcome to this tutorial on biomedical image segmentation using deep learning. I am Dr. Sonali Agrawal, along with my colleagues Dr. KP Singh, Dr. Sanjay Kumar Sonbhadra, and Mr. Narinder Singh Pun. We are here to present this tutorial based on biomedical image segmentation. We have divided this tutorial in different sections. So in the beginning, we are starting with the introductory details about biomedical image analysis. In the part 2, we are focusing upon biomedical image segmentation. Here we are discussing biomedical image segmentation along with some traditional approaches and deep learning approaches. We have also discussed certain challenges associated with biomedical image segmentation. In the part 3 of the tutorial, we are focusing upon deep learning technologies. Here we have seen how to perform the feature learning in terms of various layers. We have also discussed about biomedical image segmentation framework, along with performance metrics and the details of the loss function. The last part of the tutorial is having UNet models and its comparison with other models, along with various coverage of UNet variants, as well as certain case studies. For example, like a specific case study of COVID-19 and some other biomedical image analysis. Lastly, we have concluded this tutorial with the help of some future directions. So let us start the first part of this tutorial, that is the introductory detail. So as we all know, biomedical imaging is an essential part of the today's healthcare system for performing non-invasive diagnostic procedure. So we understand that it involves creation of visual and functional representation of the interior of the human body and its organs for clinical analysis. Usually we divide this biomedical image segmentation in terms of various aspects. For example, like it is helpful to show the internal details of human body, and it is also depicting the distribution of various physical features of the human body. It is a process by which physicians evaluate the area of the subject, that is the human body, and generally it is very difficult to visualize in our naked eyes. So this process could be a part of a clinical research or could be a part of certain diagnostic activities. So here there are two components of biomedical imaging. First is the image formation and its reconstruction, and second is the image processing and further analysis. So let us talk about image formation and reconstructions. So the purpose of image formation and reconstruction is to perform data acquisition so that we can get high quality medical images for the purpose of clinical analysis with minimum cost and without having any side effect to the patients. So this kind of image formation involves set of processes through which two-dimensional images of three-dimensional objects can be formed. Here, reconstructions rely upon a set of iterative algorithms to form two-dimensional and three-dimensional images, typically from the projection data of an object. In other hand, image processing involves the uses of the algorithm to enhance the image properties like noise removal, like enhancing certain quantitative information or enhancing certain set of features from the image for object identification or classification purpose. Let us understand different types of medical imaging. So if we see in a very broader terms, the medical imaging is divided into three different segments. So first part is the radiology based images. So here we can see ultrasound, medical resonance, computerized tomography, X-ray, 2D radiography, angiography, PET images, and fused modalities. The another category of biomedical images are visual light photography based biomedical images. Here we focus upon endoscopy and dermatology, skin visualization and some other organs in terms of visualization. We are also having one category, that is microscopy based biomedical image category. Here we see the electron microscopy, the transmission related aspects, the fluorescence, and the light based images. So these are the different types of biomedical imaging which we perform to acquire the impressions or the images of human body, so that we can analyze it for our further decision making processes. Let us understand why biomedical image analysis is important. So there are many medical applications that needs accurate labeled objects or target regions, especially in the case of CAT scans, X-rays, ultrasounds, so that it can help the diagnosis, monitoring, and treatment process. So this labeling usually it is done by the experts manually, and which is really a time consuming as well as a complex task. So there is a need of certain methodology, especially the computer vision and deep learning methodology, so that we can automate these type of tasks with the help of some computer aided systems, and that will help to have efficient diagnosis as well as the monitoring systems for better healthcare. So it is going to help not only the medical experts but also the researchers, so that they can find out faster way to adopt new technologies for better healthcare and better adoption of patient care system. So in this diagram, we can see that biomedical image analysis is divided into various steps. Mainly, these steps are having two components. So first one is the data formation. So we can understand that this is the initial task of biomedical image analysis. Here we capture the data in terms of digital image matrix. So this steps is having the first phase, that is the data acquisition phase. Here we gather the data from some real-time scenarios with the help of certain devices. And here, not only the gathering is important, but we aggregate these raw medical data, medical image data. And sometimes these images are having different modalities also. So we need to aggregate them, or we need to prepare them for further analysis. The second stage is the digitization step. So in this digitization step, we try to represent and store this imaging data with the help in terms of certain visual characteristics. So when we talk about the digitization, it is important to handle proper processing as well as compression requirements, and we have to also ensure that efficient storage has to be provided, and we also finally work for better understanding or better visualization of these images. So there are various tools, for example, like Mango, MRI Crow, 3D Slicer, or MicroDicom, and they are going to help us for these critical steps which are involved in the typical biomedical image analysis. So once we follow these steps, finally we can have better interpretation about that image, and this better interpretation may give us lead to provide certain specific healthcare to the particular patient. So it is also important to understand that now, because of some good image acquisition tools and some good digitization platforms, it becomes possible to work with medical imaging of different modalities. So that is really very important. And these different modalities are better handled with the help of deep learning models. So deep learning models are helping us for feature recommendation with the help of following task. So you can see that first task is the classification task. Classification can ascertain the presence of diseases or absence of diseases. Similarly, the another task is the detection task. Here, with the help of detection, we can identify the normal or abnormal anatomy using the bounding boxes. Whereas the segmentation is one step ahead. Here, we can generate refined boundaries around the identified reasons. And we can also have some other tasks, like we can have image registration and localization. So this all will going to help us for preparing that image for further analysis. So with the help of all these steps, we are going to train the models, and these trained models can be evaluated with the help of certain standard metrics, and it will generate some of the results or conclusion, and that can be interpreted to establish the roadmap for further treatment. So you can see that there are a very slight difference between classification, detection, and instance segmentation. So here you can say that classification will help us to understand some decision making process in terms of various classes, for example, like COVID or non-COVID. Detection is identifying the particular area with the help of certain bounding boxes, and these identified area will give us certain clue to take some specific decision about the particular situation. Then the segmentations are more precise, you can say. So they are creating some kind of boundaries, and these boundaries are going to help us to interpret that images with respect to certain context. So let us see the segmentation in more detail. So segmentation is the process of identifying and localizing the target regions within a 2D or 3D images by performing pixel level classification. So there are two types of segmentation. One is the semantic segmentation. So this semantic segmentation, it segregates the objects belonging to the different classes. For example, like background and foreground. So it is basically going to show the difference between the background images and the foreground components. Similarly, in the instance segmentation, it is same as the semantic segmentation, but it is going to have more deeper analysis, and it will also segregate the objects within the single class or common class. So here you can say that this is the input images. With the help of this segmentation, semantic segmentation, we can able to identify these chairs separately. But whenever we are doing the instance segmentation, so within that chair class, we can see the differences of the individual chair. So this is basically the semantic segmentation and instance segmentation we can analyze. Similarly, you can see the other picture where the input image, if we are doing the semantic segmentation, so it is divided into two classes only, like the background and the foreground part. But once we are performing the instant segmentation, we are having variety of views as far as the individual class is concerned. The applications of biomedical image segmentation as well as biomedical imaging is quite popular these days. So we can see that it is playing a critical role in a wide spectrum of real-world computer vision applications such as road sign detection, biomedical computational engineering, video surveillances, autonomous vehicles, pedestrian detection, and it is also widely used in various medical applications. So the use cases may be the tumor boundary extraction, the measurement of tissues volume, and it is also very much useful for various studies of COVID-19 diagnosis systems. So other than this, the another very important area of application is related to the satellite imaging and in the field of remote sensing. So here we can perform urbanization analysis and agricultural planning, and many more other applications are covered under this very trending area of research. The popularity of this research can be shown with the help of these three graphs. So you can say that this first graph is specifically prepared with the help of a Google Scholar data. And here we are trying to explain that how this unit-based approaches for biomedical image segmentations are gaining popularity. So you can see that in 2015 it was very nominal, but as the time passed, it became very much trending nowadays. And at the end of the 2021, there is a variety of applications available under this domain. Similarly, if we see the research which is other than unit-based approaches for biomedical image segmentation, so although they are having a consistent representation, but we can say that while comparing these two growth rates in terms of biomedical image segmentation, so there are more number of papers available when we especially focus in the recent year like 2020 and 2021. So it indicates that biomedical image segmentation are really a very trending area of research, and it is having a lot of potential to explore better practices, not only in the medical imaging but in terms of some other practices which can help us to create a better environment, better living standards for everyone. Thank you.
Want to thank to all the participants and the listeners in this conference. In this part of the tutorial, I'll be discussing the basics of the biomedical image segmentation. So in this section of this tutorial, I'll be discussing the biomedical image segmentation using deep learning approaches. So what actually the biomedical image segmentation is? So biomedical image segmentation is a subdomain of computer vision and image processing that aims to group similar regions or segments of an image under respective class labels. So image segmentation can be called as a combination of classification and localization, because classification is not sufficient enough to identify the interest of each. So that is why localization is also important. So image segmentation is an extension of image classification, where in addition to the classification, we must perform this localization also. Thus, we can say that image segmentation is a superset of image classification, where the model pinpoints the corresponding object that is present in the image by outlining the object's boundary. In image vision, most image segmentation models consist of, we can say, encoder-decoder network. If you compare with the single encoder network in the classifier, the encoder encodes a latent space representation of the input, which is which the decoder decodes to form segment maps. Or in other words, we can say that it maps outlining each object's location in the image. Okay. So while dealing with the image segmentation, we need to face many complexities and challenges. And few of them are, you can say that we may have images of varying dimension, structure, target tissues. And at the same time, we may have overlapped, anatomical structures also, because it is based on which type of images we are working upon. Like suppose if we talk about MRI scans or ultrasound scans are basically more complex compared to X-ray images. At the same time, we must also deal with the variations in the image acquisition settings, because suppose take an example of MRI scanning. So while taking the MRI scans, the setting is also important. At the same time, basically the directions, location, a lot of things are involved to taking the images of a particular, you can say, part of the body. But we can say that traditionally the segmentation process was carried out manually by clinical experts to eliminate the region of interest in the whole basically samples, whole volume of the samples. So thereby, it is not practical, if you are dealing with the large volume of the images. So definitely, the automation of this segmentation process is needed for faster diagnosis and treatment. And definitely, such systems are known as computer diagnosis system or CAD systems. We can conclude that image segmentation creates a pixel-wise mask of each object in the images. Okay. The goal is to basically identify the location and shape of different objects available in the image by classifying every pixel in the desired labels. So definitely, we have already concluded that yes, image segmentation is a combination of classification and localization, or you can say the object detection. So coming to the basically schematic of the biomedical image segmentation models. So initially, suppose we have images, forget about the type of images because we may have MRI images, CT scans, X-ray images, ultrasound images, and other type of images. So there is possibility that we can go for the pre-processing task first, so that we can eliminate all unnecessary things from the image, so that we can get better performance. And if we have good images, or you can say already pre-processed images, we can escape this pre-processing task. So pre-processing is basically done to eliminate this several noise, and artifacts available in the images. So for that, for pre-processing tasks, a lot of techniques are available like adaptive median filters, histogram manipulation, and others. Then the pre-processed image must go for the deep learning models. And conventionally, we can say that its unit models and its variants are the best one to do the segmentation task. And then definitely the deep learning models are able to learn the things properly. And based on the basically attain, output, we can go for the post-processing task. And ultimately, we may get the segmentation mask. So data pre-processing basically is known as, you can say, the image enhancement process, where certain set of operations are applied to overcome from the noise and other impurities available in images. And the pre-processed data is utilized to train neural segmentation network, where mostly we use UNet models or we use architectures to generate segmentation masks. The region identified region can further be refined with post-processing techniques like morphological operations, etc. So the challenges we face basically while doing segmentation or biomedical images. So the general challenges we can discuss here. So basically, if you are using deep learning models, and no deep learning models are basically best to do segmentation tasks. So definitely we must have heavy, you can say high-end hardware devices, because we need massive computation. So that is why we need heavy computational resource. At the same time, the second challenge is that the annotated data is limited, because annotation is another challenge, that how to do annotations of things or objects. And at the same time, we may basically face the multimodality adoption. Okay. So that is also one of the challenge that we must take care for better feature representation. And definitely, while taking the images, we may face low imaging quality, basically because of noise and some artifacts available in the image. And definitely, the limited interpretability of the models for a prediction is also one of the challenges that we face while doing the segmentation. So coming to the different type of images, we'll discuss specific challenges that we face while dealing with the specific type of basically imaging technique. So broadly, we can say that we may have X-ray images, CT scan, MRI scans, PET scans, and ultrasound scans. Okay, so let us come to the X-ray scan. So basically, challenge that we face is basically implicit medical knowledge to analyze 2D projection of a 3D human body. That's definitely because once you take the X-ray images, the things you'll be getting as outputs in 2D form, then how you interpret that 2D for a particular 3D object. So that is one of the biggest challenge that the radiologists face while they basically try to analyze the X-ray images. So a lot of experience is required. That is one of the biggest challenge. At the same time, it is also important that how we try to make the machine intelligent to basically, can say, analyze these 2D images on behalf of 3D images. Then large amount of pixel level annotated data is required if we want to basically segment the X-ray images. Okay. Then adopting the feature representation across various locations of human body. So definitely the feature representation is most important phenomenon for an image classification or segmentation. That is also one of the biggest challenge when dealing with the X-ray images. And this is the common challenge that we face in everywhere, every type of scans. So coming to the CT scan, basically how once we go for the CT scan imaging, so how efficiently we can locate the overlapped anatomical structures, that is the biggest issue. And at the same time, how the dynamic adaptation to the variation in the shape, size, and location of the organs, that is also one of the challenging phenomena. So coming to the MRI scans, so setting is very important in MRI scans because you cannot assure that part of a single person, if you take that MRI from two different machines, you'll be getting the same MRI scan. That is also one of the biggest challenge because setting plays a big role here. And the normal anatomical variation in the brain morphology and imperfection in the image acquisition, that is also one of the challenging tasks because you find everywhere that a person who's getting MRI scan of basically a part of his body from one basically you can say diagnostic center is different from the other one. So that is the biggest reason why these MRI basically can say experts are needed. And at the same time, the same challenges with this can say if we go for the digital version, like suppose you want to automate all these things. So again, we'll face the same problems. That is also one of the biggest challenge. Coming to PET scans, so large variation in the appearance and location of pathologies, and we can say that the limited availability of data as compared to the imaging. But as that is also one of the biggest challenge. You can say when go for the ultrasound image, that heterogeneous appearance of an organ while taking the ultrasound images, then definitely it is cannot show that yes every time you get the same type of image of an organ. That is the one of the key issues that we may face. And we may also face that we may have high intra-observer of there's a variability across different institutes and infrastructure, the manufacturers. So that is the things, these are the things that definitely will be facing if you go for the manual approach also, and the same thing is replicated with the computational approach also. But no doubt, computationally we are, can say, very strong, and can say if you able to devise good algorithms, then we may can say sure that we may resolve this issue quickly. Okay. Let us discuss the traditional approaches of the segmentation. So we may have, as you see this hierarchy, we may have threshold method, region-based method, age-based method, watershed method, and clustering-based approaches. So image segmentation originally started from the digital image processing that is coupled with optimization algorithms. And these primitive algorithms made use of methods like region growing and snake's algorithm that you might have heard. where they set up initial regions and the algorithm compared pixel values to gain an idea of the segmentation map. And the algorithms that and this method basically took a local view of the features in an image and focuses on local differences and variance in the pixels. So the algorithms that take a global view of the input image came much later on methods like adaptive thresholding, or social algorithms that we'll discuss later, and can say so. Let's discuss that what actually these traditional approaches are. So the thresholding is one of the easiest method of image segmentation. Where a threshold is set basically, for dividing pixels into two classes. It divides pixels into two classes. So the value greater than threshold are set to 1, as it is set to 0. And we can say that if you do this thing, then the image is just covered into a boundary map. Okay, so this offers basically is often used basically for image bandarization also. So image thresholding is very useful in case the difference in pixel values between the two target classes is very high, and it is easy to choose an average value as a threshold. Okay, but you may have you can say working dense images, and then this thing will not perform well. So the another approach is region-based segmentation. So here, the region-based segmentation algorithms work by looking for similarities between adjacent pixels and grouping them under a common class. Typically, the segmentation procedure starts with some pixels set as seed pixel, and the algorithm works by detecting the immediate boundaries of the seed pixels and classifying them as similar or dissimilar. The intermediate neighbors are then treated as seeds, and these steps are repeated till the entire image is segmented. Now, coming to the age-based segmentation is key. In age-based segmentation, you can say it is also called as age segmentation, age detection. You can say it's a task of detecting ages in images. From a segmentation-based viewpoint, we can say if we're looking for age detection, that we can say that age detection corresponds to classifying which pixel is an image, or can say which pixels in an image are age pixels, and singling out those age pixels under a separate class corresponding. So that is the motive of age segmentation. So age detection is generally performed by using spatial filters that give us ages of the image upon convolution. So basically, it also generates a boundary map where pixels corresponding to ages. Okay. You can say that are classified to 1, otherwise they are known as 0. Coming to the watershed-based approach. So here it basically works similar to the region-based segmentation. And images is, you can say, regarded as a topographic landscape with ridges and valleys using watershed transformer based on distance gradient marker. On here, each pixel is classified as belonging to watersheds or a region. Now, coming to the cluster-based approach, so we can say that the modern segmentation procedures that depends on image processing technique generally make use of clustering algorithm for segmentation. So basically, it works in an unsupervised manner and performs better than previous approaches. And definitely, clustering algorithm perform better than their counterparts and basically provide reasonably good segments in a small amount of time. So you can say we do not need any seed pixel here. So this is all about, you can say that all the traditional approaches. So our motive is to basically concentrate on these deep learning approaches for basically image segmentation tasks. Okay, so as we have seen that the traditional approach is already available, but why we want to move towards the deep learning approach? So in this diagram, you can easily see that if you're using the traditional approach, you must have go for a lot of things, as you have seen in earlier slides. So these deep learning models possess the potential to automatically adapt the segmentation pipeline compared to the comprising pre-processing, feature extraction selection are done by automatically, and you can say the pixels classification is can say is also done. Okay, if you compare to the traditional approaches. Okay. So that is why you can see you can see this diagram. So these deep learning models are responding to all these subtasks: pre-processing, then feature extraction, feature selection, and pixel classification, and you're ending up with the segmentation mask. So it is considered as type of, we can say that it is a representational learning, where each layer transforms the input data from the previous layer at greater abstraction level using nonlinear functions. Okay. So each successive layer extracts low to high level feature map to learn patterns associated with the region of interest. Okay. It doesn't matter which type of disease or image you are dealing with. Like suppose you are trying to do with the image tumor segmentation, nuclei segmentation, lung segmentation. Okay. So coming to the possible deep learning approaches. So we may divide any basically approach into machine learning approach into three types: okay. The supervised learning, unsupervised learning, and semi-supervised learning, or we can say that uh, weakly supervised learning. So coming to the supervised learning approaches, so if we talk about the deep learning approaches, definitely we may have backbone network along with the network block, and definitely we may have layers also, and we may have loss functions also. So if you go for the backbone network, so it's variants of UNet, you can say UNet, 3D UNet, or RNN, skip connection, cascaded 2D and 3D. Coming to this network block, we may have inception, tension, multi-scale. And coming to the loss function, it plays an important role for any particular problem or application domain. So we have a lot of, we can say, loss functions available along with, we may think for a new loss function that must be making the model more robust. Okay. Coming to the weekly supervised learning, and we can say semi-supervised learning. Basically, in supervised learning, we have labeled data, complete labeled data to learn the task. Okay. And in unsupervised domain, unsupervised learning, we do not have any labeled data. That is a complex process to learn. In between, we have semi-supervised or weekly supervised learning approach. So here, can say these are the phenomena that we must deal with, that is data augmentation, transfer learning, interactive segmentation. So basically, although the CNN shows strong adaptability for image segmentation tasks, but in fact, it is rare to build many data sets with high quality labels. So we definitely must have some supervised learning approaches. So therefore, a lot of studies on incomplete or imperfect data sets are reported. So it is having three different possibilities. You can say data augmentation, transfer learning, and interactive segmentation. So in the absence of largely labeled data sets, data augmentation is an effective solution to this problem. But for you can say large label data set is present, then this data augmentation does become more complex. So, for example, compared to the common data augmentation approaches, GAN-based approaches are currently used to work on the problem of reliance and on original data. So, That is one solution here. And you can go for the transfer learning also. Okay. So here we'll be using pre-trained models. Just used it basically for 2-minute operation also. So apart from this data augmentation and transfer learning, there is one more thing that is interactive segmentation, because manually drawing image segmentation label is usually tedious and time consuming, especially for drawing something of 3D volume data. So interactive segmentation allows clinicians to collect interactively the initially segmented image generated by a model to obtain more accurate segmentation. So for that, we have the IGS and other models in GM, that is GM, in fact. Apart from that, you can say that semi-supervised learning can use a small part of labeled data and any number of unlabeled data to train a model. And its loss function often consists of the sum of two loss functions, definitely, because we have two different things. One is labeled, one second is another that's not labeled at all. Then this is very challenging one to deal with such type of task. And the next domain is unsupervised learning. So that is the thing that we should take care while doing the segmentation. So thank you. Thank you.
Good morning to everyone. Myself KP Singh, and I'm going to cover deep learning and its variants for biomedical image segmentation. To begin with, first I would like to highlight the deep learning parts. As you all are aware that with the advent of this deep learning after 2010, many feature engineering tasks were incorporated within the network itself. And down the line, in the last 10 years, especially in the computer vision domain, deep learning models have achieved almost to the 100% accuracy. And to design every model or every algorithms, we need to be careful for the three things. In every deep learning model, we need to fix the architecture. So whatever the problem we are going to solve, we need to take the combinations of many operators to build the architecture which is suitable for a particular problem. Then we need to see how we are going to evaluate or what will be our error functions to solve that particular problem. And once the model is ready, we need optimization technique to solve the problem. These three steps are the building blocks for every learning models. Especially what happened in the convolutional neural network for image processing. A convolution model was developed to perform the operations to get the important features from the input image. You can see here in this image using convolutional network, the idea is that to define a kernel and to identify the important features which later on able to get the low level information and features which help to further classify a particular image as a horse, zebra, or dog. So this multiple layers of operations using convolution, using pooling, and then repeating this process on the different layers. This model is able to get the important features for an image, which further help to get and classify that particular image for how it is a horse, a zebra, or dog. So this structure of feature mapping is very, very important. And whatever the classification problem we want to solve, we need to design this architecture. The first component, that how many hidden layers should be there, what should be the kernel size, it should be 3 cross 3 or 5 cross 5 or whatever. Then the pooling operations we have to define. Also for the normalization part, we are going to use ReLU, sigmoid, or any other activation function that also needs to be identified. So this particular part of convolution, ReLU, pooling is essential to get a feature for each image. And this particular feature is responsible, or you can say like a representation, which using further network, we are able to clearly classify our output task. Before the deep learning, this part we used to do using many feature engineering techniques. But the advantage of deep learning is that all these feature extractions, important part or embedding, we can achieve through the network itself. So this is the architecture search, the first important component in deep learning models. Then we need evaluation technique. If problem of classification is a binary or multiple class have, accordingly we design our error function. It could be a cross entropy. And once the model is ready, we go to the third part. And in third part, basically we use a stochastic gradient descent method to solve this, or the variants of stochastic gradient, either ADAM or any other we use to solve this problem. After the success of this convolution neural network models, especially for image classification, a lot of variants of CNN is designed, like AlexNet, VGGNet, ResNet, GoogleNet, MobileNet, and DenseNet. All these models are performing very well in many, many different image classification tasks. Later on, also another kind of deep learning model, which is very, very useful in the computer vision, is encoder decoders. And encoder decoder models are very much useful, especially for segmentation 2, image segmentation part. This kind of architecture is very, very useful. In the coming slides, I'm going to explain this part. And another, in the last 5 years, a successful approach is generative adversarial network. So especially in application domain, where data sets are very less, using this GAN technique, researchers have developed a model which achieve accuracy better than the existing one. So all these three are especially also very, very important for the image segmentation part 2. The next part, I will talk about encoder-decoder architecture is one of the important deep learning architecture for image segmentation. So I will explain some basics for that. So one special variance of encoder decoder is autoencoder. And idea of autoencoder part is that if we have an image, then can we represent or get a representation for all images so that from this representation we are able to further generate the same image. So in autoencoder part, the idea is for a given input image using a network or encoder, which is a network, get a representation which using a further and other network can reproduce that same image. So the whole idea is that we want x minus x dash should be minimum. In this case, encoder function G5 could be a network, and this could also be network. This may be a CNN or any other architecture which we can use for a feature extraction, and in the same way, we can use the same kind of architecture for the decoding purpose to reproduce the images. So the idea is that this error we want to minimize, and at the same time, we have to be careful that it should not be like that. It's not an identity matrix where just passing this x to x exactly. We have to control in such a way so that the encoder representation, whatever we get, should be able to represent or get a new feature which is exactly or closer to this x. So the whole idea of this is minimizing the error between the original image, and if you see this function, this is representing encoding function and this is representing decoding function. So decoding function is giving you x dash. So the idea is that each image and their corresponding decoded image error we want to reduce, and in the bargain of that, idea is to get this compressed representation for the input. As I said, encoder decoder could be NN, CNN, VG, or any other function, any other network you can use. Once the function is ready, model is ready, then we need a technique. What I said that we can use stochastic gradient descent. So it may be a ADAM, or it may be ADAGRAD, or any other variants of the stochastic gradient technique to solve this function. So this autoencoder is used for compression as well as getting a sparse representation for a input image, which can be further used in a different applications as per need. What happened in the case of image segmentation? In the case of image segmentation, also encoder and decoder is designed, but it is not the same as autoencoder. In this case, input image is as in the autoencoder, and there is an autoencoder function G. There is a latent representation, and again there is a decoder function, but the output map is not the same as in the case of autoencoder. Here in this case, output could be any already well-known, we are talking about a supervised model, any well-known output which we have to identify from this image, and one output what we are generating from this decoder. So for any given supervised data X and Y in this case, using encoder and decoder, this Y we reproduce or get through this network, which is Y cap. And so in this case, error function is Y means for given X, the corresponding known labels are classification, it may be a pixel wise, and Y cat is classification, a pixel wise generated through this encoder decoder network. So in this case, again, we have to minimize this. The difference is this decoder is not just opposite of this, like encoder and decoder. In this encoder decoder, first component is required to get a better latent representation from the input image, and this decoder part is different than this encoder, is needed to classify or give the label for each pixel corresponding to the known labels. So in this case, the problem we can categorize as a markup problem, where the output have a fixed class or regions where we have to map that each image is going, each pixel of the image is going to belongs on which class. And accordingly, then the mapping would be done, and then segmentation will be done in the output layer. So in this case, how to design this decoder structure and also encoder structure to get the better accuracy for image segmentation is a challenging task. Many variants of this encoder as architecture and decoder as architecture has been developed, and by these variants we can say that different research has been done to achieve the better accuracy on this model. So as I said, multiple variants of encoder decoder have been developed, and one of them is for image segmentation I'm talking about, that using convolutional network. So convolutional network consists like a plain CNN, where we do multiple, you can say, from the image to all the operations like convolution, pooling, again convolution, max pooling, and again moving ahead, and then multiple times this layer we have to define how many times we want, and that's what the architectural search problem is in a different application. So in this case, once we get this representation, then the idea is to do this. Again, we have to generate each pixel class so that segmentation could be performed. So once from the low level, we have to do the unpooling and all the same kind of operation, unpooling, and then all operations what we do here in the reverse way we have to apply, and then finally we get a segmentation. So encoding layer VG16. Then what pooling here means that already the simple operations that if pooling you are performing for any input, then we can do using switch variable and pool map. And then the 4 feature we can, if we apply the max pooling, the maximum feature of 2x2 we can take as a single value. So what happened initially, if you apply the max pooling, size of the image is going to reduce. And at the same time, the many features and convolutions are going to happen. So multiple features we extract, we combine, and then in the search of, you can say, a better embedding, we do all the operations. And convolution part, so 3x3, if we are applying for the each image, we pass 3x3, and then accordingly, new feature we extract. In the deconvolution part, unpooling means, again, from the single image, let's move to the 4 variables. Here we move from 4 to 1. So here we can move 1 to 4. And then deconvolution again, what we do in the convolution, just the reverse the deconvolution. So idea is that get a better representation and then reverse engineering and better. Again, same kind of image, but here we are able to classify according to the pixel wise where it is going to belong, and then we get a segmentation. Many variants of this had been developed for a different applications. So in the medical image segmentation, in the supervised learning category, the encoder decoder is currently being widely used, and it is giving very good results compared to other models. What happened in this case, since it is supervised, so we have a data set of images and corresponding labels are segmentations are available so that we can train the model. This whole architecture can be categorized based on the different variations. And in this case, what happened that three important components, that backbone network block, and loss functions, which are very, very important to design encoder decoder in medical image segmentation. But the challenges is that, especially in the medical image domain, it contains noise, data sets, blurred boundaries in the medical images, and so it's very difficult to detect and recognize objects using very low level features. What happened in the previous autoencoder decoder model? We do the feature representation and we assume that the low level features are able to generate all the correct classification again. But especially in the image segmentation part in the medical image, where many new cases are new disease developed in the body. And so data sets are very, very less and boundaries are not clearly defined. So once we do the encoding part using the models, then only using low level features, it may not be able to perform a better recognition and segmentation in the medical image domain. So further, this encoder decoder model, especially for medical image, has been redesigned in the form of unit models, which is a special case of encoder decoder. Then, especially this unit features low level and high level image features by combining low resolution and high resolution feature map through skip connections. The idea is that to combine the embedding low level as well as input level embedding whatever we are achieving, that should be also be connected in the decoding level, so that information should be passed not from the only low level, but from the high level also to achieve the segmentation better way. So more detail about the unit will be covered by co-members. And then the variants of this unit is that this 3D net, especially the medical images are in the 3D dimensional. So in that case, this 3D unit is designed, and which is very, very helpful to achieving the better accuracy in this. And there are other variants. So especially in the supervised learning, the used architecture for encoder decoder is unit, 3D net, or kind skip connection and cascade 2D and 3D. Another important concept is that within this unit, what I said in the previous first slides, that the searching the best architecture for representation is one of the challenge. And the whole deep learning, what we do is that we connect a different architecture to get a better representation. So how this network block should be for a particular application, especially in image segmentation. That is very, very important. Dense net, which is used as a network architecture, especially in the encoding domain, to use the feature representation. This is the special case of CNN. And idea is that connect each layer of the nodes to all the previous nodes. In general, in the CNN, what we do, each layer, if we take, we connect it to previous one. But in the case of dense net, the idea is that to connect the previous one, as well as you can see that this one is a combination of 1x1 convolution, 3x3 convolution. So 1x1, then 3x3, batch normalization, and ReLU as activation function we use. And then also we are passing, if you see this purple layer, we are passing to all the information of purple to purple. So as a dense net, all one is going to be connected to the previous one. What advantage of this is such kind of network is able to produce a better representation, which may be useful to achieve a better accuracy in the different application, and also it is useful in the case of image segmentation in the biomedical imaging. But the disadvantage is, in this case, number of parameters increase. So number of parameters increase. So in that case, it takes a lot of time to optimize, and also sometimes it becomes too difficult to achieve a better result. And also due to the higher parameters and less number of training images, it leads towards the overfitting case too. So researchers have developed many variants of this network architecture. What should be used, especially in the case of a different applications. And so far it is for image segmentation too. Another variant of this architecture, which is used for representation, is inception network. And in this case, to handle that larger parameters in the dense net, what it does, it merges convolution kernels in parallel without increasing the depth of the networks. So what happened in the dense net, as the depth increase and each depth nodes are connected to previous one, what it say, okay, instead of increasing that in that parameters in that way, in this inception network, just create parallelly convolutions, or you can say the capsule, which can go like one image channel and then 3x3 convolution. Another one you can say rate convolution is 3x3, and then on top of that you apply 1x1 convolution and then a feature. Another one parallelly you can do that, a 3x3 convolution, then rate 3x3, 1x1, and then you get the features, and again you can repeat. So this one parallelly you can do a different kind of operations of convolution, 1 time, 2 time, or 3 time. Rate 3 means 3 time, and then you can make an architecture And whatever the features comes out here, then you merge and then get a features. What happened in this case, a different kind of representation, feature extraction from the original image and then mapping. It helped to reduce the features, a number of parameters. And also, since in the each one, if you see that, it uses a different scale of convolution. So it helps to get a different feature, which you can say a multi-scale convolution kernel and then getting a features. And after the fusions, it gives a better representation. So the idea of this inception network usage in the case of network block is to, in the search of better features, which further can be decoded and used as a segmentation part, the researchers have developed this model where different scale of convolution could be used. Then parallelly 4, 5, or 6 different, you can say, capsule could be developed, and then a fusion can take place, and then a new feature will be here. And after that, once the feature mapping, then the convolution, and then decoding and getting the convolution part. So the important part is that once you define that you want to use a unit for image segmentation in biomedical images, after that, for this unit, you have to choose what kind of architecture you are going to use. Then within that, variations of different networks are available. It could be a dense, it could be an inception network, or there are further also. It could be a attention-based model too. What happened further in that, and a different research is available. And the idea is to, in this case, the idea is that using the attention, can we give more importance or weightage to a particular specific feature, which could be helpful to identify or segment the pixel-wise images so that segmentation could take place. This attention-based models captures features importance for each pixel in space domain. And also it captures the importance of each pixel along the channel axis. So recently, my co-panelist members have developed this model to use this image segmentation for using this attention mechanism during this encoding part to achieve the better accuracy in segmentation. So this could be another network within the unit framework to achieve image segmentation in that domain. So once we have the two things, as I said in the first slide also, we need a model, we need an architecture. So what I said that we need a encoder-decoder architecture for segmentation. After that, the unit architecture, which steps of that will be discussed after my session. And then within that, what kind of network architecture you are going to use, accordingly your model may vary. And that's what in the deep learning beauty is. No fixed architecture is suitable for every task. So we have to do the experiment with that so that the optimal search of architecture could be done. Once it is, two things are identified, the next task is how we are going to measure the error. So how the error function could be used, and especially in the image segmentation also, what researchers are using, just I will tell you. The cross entropy loss, what is used for the classification purpose from NN to deep learning models. This is also used in the case of encoder-decoder architecture, unit architecture for image segmentation in biomedical images. And in this case, this error function compares pixel-wise the predicted category vector with the real segmentation of vector. So as we do in the cross entropy, if it is a two-class problem, each pixel we want to classify a two-class, then in that case, the cross entropy could be defined as minus p log p plus 1 minus p log 1 minus p, where p cap is a computed probability from your architecture and p is given value of the data set. So p is given, p cap we are computing, and then accordingly cross entropy we define. So error function is ready. This is the most famous even for encoder-decoder architecture 2. This is for binary class, and then same way we can extend this for the multi-class also. Another approach is, which is very much used, people are using this in segmentation, is dice loss. What it means, this metric is essentially a measure of overlap between segmentation result and corresponding ground truth. How much overlap is there? So for example, in this case, dice ranges between from 0 to 1. And 1 means the segmentation result completely overlap. So completely overlap means whatever segmentation encoder-decoder model is giving and what is exactly known with the real segmentation. So dice AB as a loss is defined as 2 into mod of A intersection B. So how much they are? If it is completely overlap, then okay. If not, then how much? Both are equal, then it will be like repetition on that. So 2 into A intersection B, and then cardinality of that upon A plus B into 100. And in this way, using this loss, we can define the error, where A is predicted segmentation result and B is real segmentation result, so which is already known, and A we are computing, and then using this dice loss, we can compute the cross entropy loss as well as, or using dice loss, we can define the error function in the encoder-decoder architecture. And after that, once the model is ready, we can use any optimization technique, ADAM or ADAGRADE or any new variants of that to get the parameters value. Okay. So if loss function is defined, then we have to evaluate how we are going to measure the accuracy or other important component of the model. So performance metrics in the image segmentation task is almost same what we use in any classification models. So we can use accuracy as true positive plus true negative upon true positive, true negative, false positive, and false negative. Or we can use precision or recall. So basically all these we can combine and say our famous one for this case or in any classification task, Either we can compute F1 score to measure that how our model is performing. Also, this specificity is very, very important. So in medical image applications, that we want that model to be this true negative and true negative upon false positive. What we want that our model performance should not be that accuracy, this precision is high, but then one class is going to be classified maybe due to the dominance of the data sets in better way, but other class should not be ignored. And so whenever that other class, maybe the other class may have the lesser number of pixel representation in the image, so that to negative class or other class would also have recognition through our model. So specificity is very, very important to measure. And for the model, F1 score as well as specificity both should be good to measure the accuracy of the model. Two famous one, especially for segmentation task, is what researchers are using is dice similarity coefficient, which is measured as 2 into true positive upon 2 into true positive plus false positive plus false negative. And another important one, which many are using, is intersection over union. So basically the idea is that P intersection G upon P union G. So in that case, true positive upon true positive plus false positive plus false negative. So these two are basically people are using, especially for image segmentation to measure the model performance. So once all the models are ready, modules are ready, encoder decoder architecture, within that the network either dense or inception or attention or any other. Then the error function, loss functions, which are being used for that segmentation. And then we need evaluation, how we are going to measure that, our model, how our model is performing for a particular segmentation task. So these three components are backbone for a supervised learning phenomena in biomedical image segmentation task. Now, what happened in this, especially in the biomedical task, and especially if we are using the deep learning models in encoder-decoder architecture, then we all know that deep learning models are data hungry. And so, if you talk about the biomedical images, many images are many kind of a special kind of disease if we are trying to segment from the image. And in that domain, if data sets are very, very less, then if we use too heavy encoder-decoder model, then it may not be able to perform better, and it will lead towards the overfit model, which is not giving a good accuracy. So one of the important challenge and issue in this load segmentation domain is how to handle this case where very few data sets, labeled data sets are available in our kitty, but we want to perform or achieve good accuracy for this small set of data sets. So within that category, researchers have developed for, especially I'm talking about the image segmentation in the biomedical. The one idea is that to use data augmentation. And in that idea is if data set is less, So augment the data, increase it, and then accordingly labels are available, and try to reduce the overfit of the model. And in that way, we try to lead towards the achieving a good accuracy. Another interesting one, model, which is very popular for this to handle such kind of low resource data sets, is to use the transfer learning. And the idea is that how we can transfer the knowledge from the model which are available for different data sets to a problem or domain where we have a very less images or data, labeled data sets. So within that category of transfer learning, the idea is that in a domain A, where we assume that huge data sets are available, so in that case, idea is use your encoder decoder model, do this feature extractor or encoding network, do this decoding for classification, and learn the model. Then a domain where we have a very less data. So how we can use this knowledge or this network or model for a domain which have lesser data, and that's where the transfer learning comes out in the play. There are many ways to transfer the knowledge, and very famous one is that, okay, this encoding and this decoding part, this is fine. Use the same network, and in this domain, one way of doing that, freeze this part. Freeze this part means don't change this feature extractor parameter value. Only this part you backpropagate. So any new domain where few images are there, the embedding will be done by the same network, but this classification task parameters will be updated through this domain where data sets are very less. So this is one of the application even in the biomedical image segmentation, where the low resource data sets are very, very less. So from other domain A, which may not be exactly same as B, but may have some kind of similarity. So we can develop a model, encoder-decoder architecture in this case, and then we can transfer the parameters, what we learned here, to the new domain, and only we can update the parameters of the decoder here. And so this model could be developed for this task B to be performed. So transfer learning and many variants of this transfer learning is nowadays researchers are using for image segmentation. And so this transfer learning is classified in many different cases. So one case is labeled data are available in a target domain. So this could be, we can say, as a source domain, and this could be, you can say, the target domain. So if in the target domain, we have a labeled data, means 1 or 2 or 3 or 10, 20 images are, and for each image, segmentations are available. That's what the target data. And then again, this transfer learning can be classified in a different problem where the target domain have labeled data. Then one case is that no labeled data in the source domain, where in the source domain, all images are there, but no classification. And if we are going to do the transfer of knowledge from such kind of source where no labels are available to a target where few images with labels are available, this can lead to a self-taught learning domain, and many work has been done as a self-taught learning model development, which could be further used in the image segmentation tool. Another case, what happened in the multitask learning, where this is available and the source task also have the label. So be careful. In the self-taught, source domain have no label, but in the task where the target have the label and source have label, so this could lead to a problem where our setting, which is known as multitask learning. So this multitask learning could be deployed here to achieve a better accuracy in a domain on a problem where lesser number of images are available. Another case where different domain and in the source domain labels are available, but here no segmentation is available. So in that case, domain adoption could be performed. And further, so what happened based on the availability of labeled information, the data sets are the whole setting of the problem we can categorize as in the self-taught to multitask to domain adoption to sample selection bias. And currently researchers have deployed this a model where a pre-trained model, basically, where a model encoder decoder is developed for a source task, and then it is freezed like this defined structure here. Encoder is freed and then decoder is only trained. Other could also be used for this task of image segmentation. Further, currently, all the works of this is based on either a self-taught or multitask, but this problem could be solved using a meta-set learning and few shot learning setting. So this is still very few work or almost nil work has been in this way to solve this image segmentation using a few shot, means where a domain where we want to solve the problem, we have only one labeled case. So especially in the biomedical images, collecting the same kind of images and segmentation from the different humans is not so easy. So can we develop a model from that 1, 2, or 3 images which are labeled? Can we develop a model which can give a good accuracy for any new images for the same kind if comes out? So the transfer learning, especially few shot learning and meta learning, and that image segmentation in the biomedical domain could be one of the important future direction which can be used to solve this problem. So with this, thank you all for this session. And my co-panel member is going to further cover the next detail of UNET and the case study for solving biomedical image segmentation using especially UNET models. Thank you all.
Greetings everyone. Now we will begin with our fifth section, which covers various biomedical image segmentation models. In the earlier section, we have seen that the UNET model is very widely utilized for biomedical image segmentation. And now we shall see some details about UNET model, following its disadvantages and different types of unit-based models. The UNET model proposed by Ronberger in 2015 is named like this due to its U-shaped architecture as shown in this figure. This model was observed to achieve state-of-the-art performance in one of the renowned open source benchmark challenge, which is known as ISBI Self-Tracking Challenge, where the objective is to segment and track the moving cells. Due to this model sets up the foundation for various biomedical image segmentation applications. This state-of-the-art behavior of the unit model is observed due to its modular structure, following symmetric contraction and expansion paths where corresponding layers are concatenated via skip connections to effectively capture feature correlations. We shall now see each of these components in detail. At first, we have an input layer and output generated by the model from the output layer. The input layer defines the dimension of the input size of an image, which can either be 2D or 3D. This acts as an input feature map to the model. The model performs computations on this input and generates the corresponding binary mask where regions of interest or target regions are classified with pixel value of 1. Generally, the input and output spatial dimensions are kept same so that the mask can be localized easily on the input image. As shown in this figure of segmentation results, given the input image A, we got segmentation as shown in image B. And similarly, given an input image C, we got segmentation results as shown in image D. These results are taken from the main unit paper. Now let's move to the contraction phase. This phase comes into action after input layer, where we tend to learn the feature representation of the target regions. This is also known as feature extraction phase. In the proposed unit model, there are 4 stages, where each stage comprises of stack of ReLU-activated convolution operation to extract the feature maps and then the max pooling operation to downsample the feature maps. After the processing at each stage, the spatial dimensions of the feature maps reduces by half and depth of the channel increases by multiple of 2. Later, we will see the features extracted at each of these stages are also propagated to encoder block or the expansion phase that is used for the reconstruction of the feature maps. As shown in this schematic representation of the unit model, the convolution operations are represented with blue arrows and the corresponding output with blue blocks, and also the max pooling operation connecting each stage is represented with red arrows. After the contraction phase, we have bottleneck layer. This acts as a bridge between contraction phase and the expansion phase. It helps to propagate the feature maps with the cascaded convolution operations without max pooling from encoded phase to the decoding phase. Here the idea is to learn useful information from the encoded feature maps representing some useful information. These feature maps are then transferred to the expansion phase to reconstruct the spatial dimensions and generate the corresponding segmentation mask in the output. Now we have the expansion phase, which is also known as reconstruction phase. Here the aim is to upsample the feature maps and generate the segmentation mask in dimensions similar to input. As in the contraction phase, this also has 4 stages. Before moving to each stage, we first perform upsampling operation that tend to increase the width and height of the feature map by a multiple of 2. These upsampled feature maps are then processed with ReLU-activated convolution operation, where the depth of the channel is reduced by half. Additionally, we also make use of skip connections to efficiently utilize previously learned features while reconstructing the feature maps. The skip connections enables the network to transfer the encoded feature maps in the contraction phase to the corresponding decoder layer in the reconstruction phase. As shown with the gray arrows left to right, these long skip connections enables the network to gradually capture long-range dependencies in the feature maps. At each stage, the feature maps from the upsampling operation and skip connections are concatenated along the channel axis and then are processed with the convolution operation. This is just an example that illustrates how these operations are executed. For upsampling or transposed convolution, consider the input feature map of size 2 cross 2 and a kernel of size 2 cross 2. Here, stride is kept 1 and padding is kept as 0. Now for each input pixel, kernel is multiplied. For example, in first intermediate matrix, input 0 is multiplied with complete kernel, and then filter moves with stride 1, and the input 1 is multiplied with all kernel weights, and so on. The resultant 3 cross 3 matrix is obtained by adding all the intermediate matrices. For convolution operation, consider input of size 3 cross 3 and a kernel of size 2 cross 2. Here also stride is kept 1 and padding is kept as 0. Now we move the window of kernel in the feature map and perform element-wise multiplication and addition with the kernel weights. This kernel window moves around the feature map and resulting 2 cross 2 matrix is generated. For max pooling, consider we have an input of 4 cross 4 and a window of size 2 cross 2. This window extracts the max value from the input feature map, considering the input values within that window. For example, in the first window, max value is 6, then in the second is 8, and then it is 3 and 4. In unit model, another achievement was to convert segmentation problem into a classification problem where each pixel is classified to belong to a certain class. Furthermore, the model uses weighted binary cross entropy function following from the softmax activation. This function converts the output activations into probability distributions concerning the available classes. The binary cross entropy function is then used to compute the error in the prediction where Wx represents the pixel weight, Gx represents the ground truth, and Px represents the predicted probability. This weight was introduced to segregate the overlapping boundaries in the output mask. This weight map can be computed using this equation where D1 and D2 indicate the distance of a pixel to the nearest and the second nearest boundary. The sample weight map is presented in this figure. Finally, using the computed error, the training parameters are fine-tuned to achieve the minimum error. UNet has been observed to be the most suitable segmentation model in the area of biomedical image analysis. However, there are several other models that are used for segmentation such as mask RCNN, DeepLab, SegNet, etc. Now, let's first see about mask RCNN. This model is very widely used for instance segmentation tasks in computer vision field. It adds fully convolutional network to faster RCNN model to generate masks for each object, where faster RCNN model is an object detection model that draws bounding boxes around the objects or target regions. As shown in this figure, the overall model is divided into two stages, where first stage generates proposal about the region where there might be an object based on an input image, and the second stage uses these proposals to predict the class of the object, refines the bounding box, and generates a mask at pixel level of the object. The major components of this model are a backbone model, a region proposal network, a region of interest alignment layer, a bounding box object detection head, and a mask generation head. With backbone, we have some feature extraction layers. Following this, we make use of anchor boxes in the region proposal networks to localize the objects in the feature maps. Now the region of interest alignment extracts the feature vectors from the feature map based on ROI proposed by the RPN and turn them into a fixed size tensor for further processing. After we get individual ROI feature maps, we can predict its object category and a finer instance bounding box. And finally, on the mask generation branch, we feed ROI feature maps to the decoding layer and a convolution layer successfully, as we have done in UNet to generate final mask. More details about this model can be found in the paper by Gaming He as shown in the below reference. Now, Deep Lab is another family of segmentation models that have improved over the years, where each phase of enhancement is named as Deep Lab V1, Deep Lab V2, Deep Lab V3, and Deep Lab V3+. In Deep Lab V1, some backbone models such as VGG16 is used for feature extraction, where the pooling layers are replaced with newly introduced Atroz convolution. In this convolution, in order to increase the coverage or the receptive field of the network while not increasing the parameters, we can pad each filter weight with zeros. For example, as shown in this figure, where A is a 3x3 standard kernel without dilation and B is a dilated kernel of size 3x3, having zero padding around the pixel weights. You can also observe in the below animation how this filter extracts the desired features with wider receptive field. To further improve the results, Deep Lab V2 proposed Atroz spatial pyramid pooling module that captures the features with multiple dilation rates and computes the aggregated feature maps that represents multi-scale feature learning. Later, in Deep Lab V3, multiple ASPP blocks are used to generate much better segmentation results. Deep Lab V3 Plus further extends the Deep Lab V3 with a decoder block to improve the segmentation results. It also used depth-wise separable convolution to address the problem of complex computations. These, other than unit models, are very widely utilized in integration with the standard unit model for various biomedical image segmentation tasks that addresses several disadvantages or problems associated with the vanilla unit model. Despite vanilla unit being super efficient in the ISBI cell tracking challenge, there is still a void to fill with improvements in certain aspects. The most apparent problem in the vanilla unit is that the learning may slow down in the deeper layers of the unit model, which increases the possibility of the network ignoring the layers representing abstract features of the target structure. This slack in the learning process is due to the generation of dilated gradients in the deeper layers. Another major issue is concerned with the localized convolution, which tend to limit the capability of the model to efficiently capture global and long-range dependencies. Furthermore, the distinct challenges introduced in performing segmentation using different modalities needs to be addressed, which however is not optimal with standard unit model such as limited data availability, high variation in the target structure, etc. Now let's see how various unit variants are introduced. Mostly, the variants are developed to address the challenges associated with the task at hand and also to address the problems associated with prevailing models. Due to the easily mutable and modular structure of the unit, we can easily modify the network as per our requirements. Following the existing variants, most of the unit model are introduced by modifying the way convolution and pooling operations are conducted. For instance, depth-wise separable convolutions are computational friendly as compared to the standard convolution, and spectral pooling is a better option to preserve more information while downsampling the feature maps. Another aspect which is considered is how individual blocks are interconnected, such as they can be in densely connected or they can follow inception connections, etc. Another aspect to see is how to propagate feature maps from the encoded layer to the decoded layer. Such as in skip connections, several attention filters have been introduced. There can also be ensemble learning where we can combine the segmentation results of multiple models, and there can also be a possibility of integrating other models into the unit model such as GAN based unit, transformer based unit, etc. Now let's see some of these modifications. As shown in this figure, for dense connection networks, the input of each layer comes from the output of all previous layers in the process of forward transmission with the help of concatenation operation. This enables the network to capture global context of the feature maps effectively. Next, we have residual skip connections, These are also termed as short skip connections. It is most widely utilized to address the problem of vanishing gradient in deep neural networks. As you can see in this figure, after two yellow blocks of convolution, we also perform addition with previous activation. This adds the option for the feature maps either to use those blocks of convolution or skip them to move to next block. While following the fact that deep networks often give better performance than shallow ones, in another form of unit variants, inception convolutions are introduced that aims to improve the performance of the model to capture multi-scale feature representations at a single level. Here, the idea is that if you have variable size target structure, then we need to have a dynamic receptive field such that model can adapt automatically which filter size to use. Hence, to do this at a single level, we perform multiple convolutions with different filter sizes and then concatenate them along the channel axis to generate final extracted feature maps. As you can see here in this figure, there are four parallel paths and each path represents different set of convolution operations, thereby enabling the network to choose which path is appropriate for given feature maps. And in another variant, attention filters can be added in the skip connections to make model focus on most relevant regions in the feature maps concerning the target regions. Here in this figure we have shown mixed attention filter that performs channel attention and then spatial attention of the input feature maps to generate mixed attention maps for better feature representation and overall learning. This is another modification aspect where unit is acting as a generator to output binary segmentation mask, and there is another encoding path that acts as a discriminator to understand whether the binary mask produced is a real or fake. Overall, this framework follows adversarial training scheme that learns by making the discriminator network fool enough that it fails to identify the difference between the real and fake or generated mask. In this framework, there are a lot of variants available to work with different biomedical image segmentation tasks. Now these are some of the popular unit variants that are introduced for biomedical image segmentation across various modalities. Additionally, we have also highlighted their implementation strategies such as transfer learning or training from scratch and whether any pre-processing or post-processing techniques were used. In early models, most of the approaches tend to establish the potential of vanilla unit model with various modalities while using transfer learning approach. For instance, three others utilized unit with pre-trained VGT16 model for segmentation using X-ray imaging. Proposed by Zhou and others, UNet++ is another major improvement over vanilla unit that follows convolution on dense and nested skip connections to effectively capture the coarser details. In another approach by Abetla and others, two-stage training approach is proposed where initially model is trained with half resolution of feature maps and later network is fine-tuned with full resolution images. It is well known that COVID-19 brought worldwide crisis and the problem has still not resolved completely. Experts, clinicians, researchers have been constantly working to come up with some concrete solution. Following the current advancements in deep learning technologies, various unit-based approaches are also introduced to help in diagnosing the COVID-19 faster using various modalities such as CT and X-ray imaging. In order to segment the COVID-19 infected regions in the lungs, a unit-based hierarchical segmentation framework is introduced as CHS-NET, which is known as COVID-19 Hierarchical Segmentation Framework. In this approach, two cascaded attention-based unit models are used, where first model generates lungs segmentation mask and second model uses those masks to segment infected regions. In another approach, hybrid classification and segmentation framework is introduced, where group ASPP framework is used along with the attention filters to generate infection segmentation masks using CT imaging. There are several other approaches based on transfer learning, deep supervision, ensemble learning, etc. for faster diagnosis of COVID-19. Based on the protocols introduced to control the spread of the COVID-19, various measures were introduced, and following those protocols, various AI-assisted frameworks are also developed. For instance, automatic social distancing monitoring framework, face mask segmentation, localization of false information, exponential growth trend analysis, segmentation of highly contagious regions, and etc. Now, these are some other case studies of UNET model where we are showing the segmentation of nuclei, then brain tumor segmentation, and anatomy segmentation, where we have shown lung segmentation using CT imaging. Then there is skin lesion segmentation using dermoscopic imaging. Then we have blood vessel segmentation on retinal blood vessel images, and then we have breast cancer segmentation using ultrasound imaging. Then we are identifying the anomaly segmentation for fracture identification. There are a lot of such applications of UNET in biomedical image analysis. Now we are at the final part of the tutorial where we will cover our future research directions and concluding remarks in the area of biomedical image segmentation. In future, we can extend with several improvements in the UNET-based segmentation models by integrating it with other deep learning modules to perform biomedical image segmentation on other medical imaging like MRI, X-ray, PET, etc. To address the harmfulness of radiation based on imaging such as CT, MRI, or PET, modality transformation-based approaches can also be explored, which can later be tuned with multimodality fusion-based segmentation approaches. Multitask context-aware approaches are also promising and have a huge scope of further improvement. In most of the applications, the model interpretation part is mostly overlooked. Hence, more emphasis can be given to such approaches for real-time computer-aided diagnosis systems. As we have discussed, UNET models follows mutable and modular structure, which makes it very easy to modify and integrate with several other deep learning based computer vision technologies. We have also seen some advancements practices that can be incorporated and further improved in UNET models such as attention filters, multi-scale feature representation learning, ensemble learning, integration with other state-of-the-art models, and much more. The potential of UNET model can also be extended to other application domains that require segmentation of objects and regions, such as autonomous driving, anomaly segmentation, etc. In addition, since deep learning models are not resource friendly, we can design some framework with minimal resource requirements to make it fit for deployment in the real world. Moreover, we can also reduce the dependency of the deep learning models on large amount of annotated data samples with the help of emerging self-supervised learning strategies. The advancements in deep learning approaches, especially UNET, has encouraged researchers to contribute towards biomedical image segmentation domain for the development of computer-aided diagnosis systems. The state-of-the-art performance of UNET model for biomedical image segmentation, along with its easy mutability, has attracted many researchers for the development of various UNET variants. Due to its flexible structure, more efficient variants of UNET can be introduced by integrating various state-of-the-art deep learning models and training strategies. These models can be easily interpreted with the help of visualization techniques such as class activation maps and uncertainty maps. More emphasis can also be given towards realization of the developed models for real-time application. And these are some references that you can use to get more knowledge about the research in the area of biomedical image segmentation. So, thank you.